Dear God. Okay, keep searching. What's the next? What?
ESH or that? Don't see it on here. Oh, Ready to Die, the Notorious.
Mm-hmm.
Okay,
Yeah, maybe heard of him?
yes.
The Large? The Notorious Large? Okay. Hi everyone. Look at everyone here early. How's everyone doing? Like good, huh?
Yeah, weekend was good.
Weekend's good? You got all the homeworks done? Get any of the homeworks done? Is that homeworks? That's he's pulling out papers.
One home.
One homework?
Homework six.
Let's go. Cash dollars.
I don't have my name.
That's a... Okay. How's everyone doing?
Need to log in last 3 weeks. That's fine. So seriously. Start off strong, then I got beat, and then
You got
finish
beat?
off- or finish strong, finish off strong again.
Why did you get beat?
It's just
Just life being like that?
busy.
Yeah, that's true. What's nice is it doesn't get better.
It does. That's probably not better.
End of the semester's coming up, and that's really nice. That gives our brains a nice reset. We go to grad school, and the first 2 years are harder, and then the next 3 to 5 years are easier.
Yes.
So there is a little bit of a break. And of course, there's the time in between. And if you decide to go into academia, then you get breaks. If you decide to go into industry, no more breaks, just work. And of course, the nice thing about academia is you have breaks. The nice thing about industry is you actually make money. So turns out you got to work for that cash, you know. So, I think we're either gonna finish this discussion of internal waves. So talking about like how do waves form here in a stably stratified fluid. And I kind of just showed you the run by solid frequency. But I didn't quite tell you what it was or show how it comes to be, or more importantly, how it's used. I think we don't want to spend a ton of time on that. Just because how much time we have left in the semester. But essentially, what we were trying to do, or what I was trying to show, is how to linearize differential equations. So what we mean by linearize is to say that solutions have a form such that there is some first order P, which is a result of the average plus a perturbation. Okay. And this is a very standard form or standard method of solving equations. Because what you can do is you take this thing here, which is the average, and you're going to get some typical profile from it. So for example, we had something that was sorry folks online, but I'm turning off the screen really quick. We had something which was like this, dw dt, which is the vertical transport, right? And that was only a result of the density perturbations. So something like the vertical gradient, right? And the restoring force due to gravity. Okay. And what we can do is we can say to ourselves, okay, so if there is some perturbation from the normal, then first we can solve this. And we can say to first order, I believe that this thing will be 0. Right? And this is kind of a weird way to think about physics. So you say, okay, let's break this into a series of the more important pieces of the profile. And so to first order, this is 0 plus some perturbation, right? Some little like delta, some change to 0. And that can be positive or negative, of course, right? And then really what you're trying to do is you're trying to solve this thing for the 0 component and this thing for the delta component, right? And the only reason why I'm going over this is not so that we go through the process of solving this type of equation today, but so that you see this process of how we, like in practice, actually solve differential equations. Because you usually start off with something like this, right? Where, okay, that's not like generally easy. But if I set this equal to 0, then that does become quite easy because I can make some approximations regarding p and rho. You know, I can relate them using the scale heights. And if this thing is 0, then I naturally get something like e to the minus x, oops, let's do c, z over h, right? P, something like that. Some scale height for the atmosphere. And that's sort of something that we did in statics in the very first week of class. So we can go back and we can use that solution, which is this. And then all we have to do is we just have to add on some perturbation to it, right? So solving for the perturbation is pretty straightforward. I introduced this thing called n squared. Okay, n squared is minus g over rho naught, where rho naught is the density or the sort of like averaged density at a given time period at a given place. And then it's something like the vertical gradient of the density itself, the average density. Okay. If we define this thing here, okay, then we can write the following. Let's see, how many steps do I want to do this in? I think I'm gonna jump to the chase here, if that's okay. The full derivation is on page 394. But the idea is this leads to a series of equations, and you can kind of see how they're going to end up looking anyway. You have something like this like d vertical speed with respect to time. How does that change with respect to time? What's the vertical acceleration? And we say, well, this is due to gradients in the pressure and maybe wherever you are, the local density, right? But things like the local pressures, well, they're related to the vertical gradients in W. Because remember, we said in this idea, the whole atmosphere is constant in the horizontal and the only variations are in the vertical, right? So the sources of pressure then are from motions in the vertical, right? And what this ends up giving us is something a little fun looking. You have a horizontal Laplacian. So you have to define something like this, which would be okay. Now that is just for the horizontal. There's no z there component, even though there should be. And most importantly, you get something like del squared del t squared. And it's going to look something like this. This is the real Laplacian, okay, plus n squared del squared h equals 0. Okay. This is weird looking, right? You maybe don't have some intuition for this, or maybe you do. You stare at it for a few seconds. Does it remind you of anything? Okay, I like that idea. Yeah, there's something like a time term and something with space. That's not what I'm going for. Let me show you this thing instead. What?
The solution is E again.
Is it?
Oh, no, it's times.
What kind of equation is that?
Here's our second one.
It's definitely a second order equation, good. Second order in time, second order in space. But it has a name. This one you've seen before. I keep trying to do that. What's this one?
That looks like vorticity, but it's not.
Okay, so you know this one. What's it start with?
What you're looking for.
How would you solve this equation? What is F? What? This is not a V. Let's use this as like just a constant. Let's use whatever we want. Squiggle sign. Blorp. What? Blorp. Blorp, yeah, blorp. So the second derivative with respect to time of F plus blorp F equals 0. Or this is equivalent to has the same type of solution as this one.
The V that we did with the sign.
What?
We had something that was like F double prime equals some constant times double prime. Where is that?
Yeah. F double prime equals some constant times F gives you the solution of
AE plus B.
right. Sinusoidal, right? So this one must be sinusoidal because in fact I have a plus here. So I move it over, right? The function taking two derivatives gives you the function back. Is either sine or cosine or complex exponentials, right? So this is some periodic function. So this could be sine, this could be cosine, or this could be e to the I theta, right? Okay, what's this one? Interestingly enough, this is called the diffusion equation. And its solution has exponentials. Now, interestingly enough, these exponentials, okay, they are not growing because that wouldn't be diffusion. They are decaying. Okay. And as we take one step up, right? Okay, we combine these types of behaviors. Now we have two spatial derivatives and two time derivatives. These also use exponentials or sinusoids, and this is the generalized wave equation. Those periodic functions. Good. Does that differential structure make sense? Okay. So have a look at what we have here. I have some DDT, okay, of something that looks like the Laplacian of W. And then I have n squared. Now n squared is a number. Times the horizontal Laplacian of W. Okay. So that looks like something in between this and that. Right? Like a weird mix between that. Right? You see the similarities? Yeah. L squared something times this thing. Right? They're not the same. They're just similar. Right? Okay. Well, what this allows us to do is it allows us to take this equation W and create a dispersion relationship. So it allows us to understand how waves that are propagating in this internally stratified medium, how they propagate with respect to the wave number. Okay. And it's pretty cool. It's quite straightforward actually. The simplest way to write this is that omega is equal to K over capital K times N. Now K is the direction of the wave number, so these can be three-dimensional waves. Okay. And N is the maximum possible frequency of internal waves in a stratified fluid. So what this N indicates is the max frequency of waves in a okay. And what you end up with is essentially something that looks like waves this type. So you're gonna have something that looks like this is sorry, omega, not W, and I'm gonna write W now. We're gonna write W with a little bar next to it, just to clarify, like this.
But in this case, capital.
Yeah,
Okay.
that's bigger, right?
I was just like, why is it not?
How should okay, should I do it like this?
Yeah.
Is that better? Okay, so it's little k over big K. Just fuck that out. I'm sorry. Okay, so here's your W, and let me just clear up the W. Okay, so this is different than omega. Because everyone knows my handwriting is shite. Okay, so this is omega, right? And this W is something like some vertical structure times e to the I K, this will be the capital K that we're using, dotted into X vector which is like just the directional vector, wherever we're headed, minus omega t. Okay. So what this means is that you essentially have on some internally stratified media, that is, if you have layers of something that's stable on top of each other, waves can propagate in it. And they can propagate in any direction, with buoyancy being the restoring force and pressure being the, like let's say you have something that is overly dense, it goes up, then you're going to have the gravity's pulling it back down and buoyancy pushing it up, depending on what its relative density is to its neighbors, right? And that is kind of modified here because you have something in here, W naught e to the ikx. Okay, so one thing that you can notice right away, let's see, maybe you don't notice it right away. Let me say this different. E to the I is a funny like partner to have in science because it can change what its behavior is based on its argument. What are the two behaviors of E to the I something?
You like positive and negative.
You think that's it, right? Think that's
But negative pops it back to.
Okay, let's try. Let's try some options here, okay? So let's say the function is e to the I, what?
2.
Okay, yeah, let's do 2. Now, I'm gonna go ahead, I'm gonna be a little bit more gratuitous here. I'm gonna do I, and I'm just gonna say t when t is greater than 0. What does that behave like? Like when you
Looks
graph
like
it
a
out?
curve.
Yeah, look what kind of curve?
Was it close? Sign?
So yeah, so it doesn't matter. It looks like this, right? And the idea of sine or cosine is now irrelevant. We have graduated from the idea of sines and cosines. We're smarter than sines and cosines. Sines and cosines is a trick. The trick they played on you in trigonometry. Because it's the same fucking function. You just add plus 90 degrees, or you just add pi over 2. That's garbage. No, they are complex exponentials. Right? And so you say to yourself, oh, that's cool. Okay, now that I recognize that, when I see this, I'm just thinking this shape. I'm not even thinking sines and cosines anymore. I'm thinking periodic function. I'm thinking sines and cosines like this, right? So let me ask you a different question. What about when t is less than 0?
Yeah, but the sign, I did like the weights now. Like overlapping, but in between, yeah.
Very good. Okay.
That was kind of fun.
No, it's great. It's great. I got it based on that. You're like, and you're like moving your hands, so I can figure that out. Good. So you did it, right? You figured out all the potential solutions to e to the I theta, right? Or e to the IT. Ah, there is one more. What is it? 2. No. Sorry. That's a boring one. I don't like that. That's not like a behavior of a function. Right? E to the IT, this becomes 0, this becomes 1, f is just a constant, right? So you're right. Okay, there's a 5th one. Okay. But I don't like this. Not the one I
If we have the t is something that's also a function.
That's maybe too complicated. I'm just thinking about what are the potential solutions for this for different values of t. Did we do it? Did we cover all possible t? I said t strictly greater than 0. You said t equals 0. You said t less than 0.
This is for real t.
Ah, is this for real t? Do we have any constraints on t? The answer is no. T is a number. So, real number, imaginary number, sure, we may not have a way to interpret that just yet. But what makes the complex exponential so incredible and so powerful for this type of mathematics is that we have 4 solutions. So what about t greater than, well, yeah.
So I'm thinking I negative I.
Yeah, I would do something like this, right?
Oh, right.
Right? So what if it is a complex positive? What?
Does it go in and out of the board?
No, what, look, take this number and plug it in here.
You got I
squared.
Which is?
It looks the same as t.
No. Can't bring down. Yeah.
What's I squared, folks?
Negative 1.
-1. So your sinusoidal form becomes?
Same as t less than 0.
No. The sinusoidal form, if this becomes -1,
Just exponential.
is a negative exponential. Right? Do you see that yet? Okay, what about the other case? A positive exponential. What the fuck? So this one form has 4 solutions, right? So now we just have to determine whether or not the coefficient to a complex exponential can also be complex. Is that possible? What? Yeah. Right? So let's imagine a world in which W as a function of K. Let's do something like that. Have we ever done something like that before? Yeah, and maybe it's something like I don't know, A minus B. Right? If A is larger than B, what do you get?
Positive. Change.
Okay, hold on, let me say this differently, okay? Here's your solution, okay? Let's imagine that this is the solution. I omega t.
Then you'll get solution of t greater than 0.
Which is a
Sinusoidal.
sinusoidal. Good. So if A is greater than B, then you get sinusoidal solutions. What if B is greater than A?
Get your imaginary. Exponential.
You get exponential solutions. So with the same equation, you can get waves and you can get explosions. Right? The same physics supports it. And that's what's beautiful about this. You see this equation here? You have W. This W naught times e to the I kx omega t. And k and x, you know, they can be related by the dispersion equation. And the dispersion equation is not required to be real. No requirements that it's real. Okay. It's crazy, right?
How come math called it imaginary? They didn't know it's applicable yet,
What?
so how come we call it imaginary?
Because it's not on the real line?
I know, but why, I mean, who thought of that? You think imaginary doesn't exist in real?
Well, imaginary not meaning like, like, Japan, right? That's not what imaginary means. Imaginary means there must be some number such that when I take the square root of -1, I get a result, right? So it is papering over an issue. And the issue is that no two things multiplied together, the same thing, give you a negative number.
But is that because of our definition of square root, or that's just how it works?
Well, both are a reflection of the fact that mathematics is not just created, right? Some people believe that mathematics is discovered. So how it is that numbers exist is a fundamental philosophical discussion that people have, right? Did we discover zero or was it always there? Would other civilizations have a zero? Right? Because nothing is not a thing. Nothing was one of the last numbers to be created. It's not a concept, right? You can't represent that on your fingers. You can't count the absence of something. You can take things away, right? So the idea of negative numbers was even a stretch, right? And we've kind of gotten used to that. And it's simply an extension of that frame of logic. So as you look at a negative number, you are suddenly created with an issue, which is that no two things create the negative number. And so you need to invent I. Now, why don't you need something like a J for the I's issues that it creates? Well, thankfully, there's a beautiful symmetry there.
Yeah.
Two I's give you -1. And of course, more than one I just gives you -1 I. Right? Let's say 3 I's is -1 I, which is still part of the number line. So you don't need to get more complex than that. And suddenly they found out that if you just add I, if you just add another dimension to the real space, you get all actual numbers, real and imaginary. Mathematicians, so they would call this like R1 would be the number line, R2 would be the number line and the imaginary line. But Rn is imagining any number of dimensions, right? So you can do all of the work that you see in more than 1D, right? Including the types of like people give a lot of shit about numbers. Think about things like topography and manifolds and all this garbage that may or may not have any physical interpretation. But in order to do something like general relativity, Einstein had to wait until the mathematics was generated that he could use to describe the laws of gravitation. So in many, many cases, we are limited by our language and the language of mathematics. So mathematicians sort of press off into directions that they don't even care where they're going. And every once in a while, physicist goes, "Huh, wait, I can use that," you know? All right. That's a lot of, we already got me yapping a lot this morning. All right. So I really want to show you. Okay. You can write this in terms of omega, you can write this in terms of k. Right? This is n. This is n squared. Do you see a problem yet?
Figure square root of negative.
Ah, you're taking the square root of a negative. So this thing here is your saving grace, right? So this physical thing, del rho del z. If that's negative, then this cancels, and this thing here is nice and real. Okay? And it's nice and real. We go into here, bada bing, bada boom. You get waves. What happens if it's not real? That means that this thing was positive. Right? So this is going back to the physics of what we're talking about here. Okay? So what I'm saying is del rho del z. This is talking about how the temperature, the density is changing as a function of height. Okay? And as you go up, does the density go down? Right? Because rise over run. So when do you get a negative slope here? As you go up, density goes down, right? D rho dz. Okay, so think about it this way. I have some parcel. Okay, here's a parcel of gas. It rises. Okay, it looks around and it sees that the rest of the air around it now is lighter than it is. And it comes back down. Right? It might have speed. It might pick up speed as it goes down, and it overshoots where it came from, and it sinks further. And then it looks around and it sees, now I'm lighter than all of my peers. And the buoyant force restores it. Right? And that sends it back up through the equilibrium point. And we have created a wave. You see the buoyant force being the restoring power here? Let's try a new one. I take my gas ball. I lift it up. It looks around, expecting to see that it's now lighter than its friends. Or sorry, expecting to see that it's now heavier than its friends, and it's not. Now what happens?
It thinks, but it's not.
Well, it looks around, right? Because it's comparing to its last time when it was bouncing around all fun and joyful. So last time when we did this, we picked it up to a new height. It looked around, it saw that it was heavier than its friends, and it sank. But now we lift it up, it looks around, and in fact, it's lighter than its friends.
It should go up.
It should keep going, no? What is that motion? You see? It looks around.
Yeah.
It looks around. It sees that it's lighter than its friend, and it keeps going. And it keeps going, and it keeps going, and it keeps going.
So its partial z is positive.
Yeah,
Oh, we can go. I see.
it's going up. This is an example of runaway, right? Now, does this happen for the entire atmosphere? No. This only happens when the slope is positive. And if you have something, what the fuck did my happen? Okay. Ready? Temperature gradient. Rough approximation for the density gradient. What's the slope here? Negative. We're all happy with that? Hotter at the bottom, colder at the top? What exists in here? What kind of possible states?
Solid.
What?
Solid.
No, this is still an atmosphere, this is still fluid. What kind of states for the types of internal waves that we're talking about? Which of these 4 different options? In this region, del rho, del z is here?
Greater than 0.
It's definitely not greater than 0, folks. This would be greater than 0, no? This is less than 0.
Oh, I think it will.
Right? So if it's less than 0, then you get what kind of thing? Waves. Right? The restoring force is gravity. So I start with a little parcel of gas and I raise it up and it looks around and it sees that it's heavier than its peers and it sinks. And so on and so forth, right? Now, what if you have a temperature inversion? What? Yeah, the temperature inversion. Like, what if it does this? Oh my god, and I wrote this backwards. Wow, I'm helping you. I'm completely fucking. I didn't write what we're writing here. Okay, hold on. Okay, this is Z.
Okay, see,
This is rho. Okay, so now let's write it from the bottom again. Okay, if this is Z and this is rho, then we need to turn our heads to make that same picture. And then this is d rho dz. Greater than 0, right?
okay, I was about to say.
Okay.
That's pretty.
Just make sure that we're doing it properly, because I just wrote it wrong on the board and I explained it wrong.
Yeah.
Okay, so Z is vertical instead of being horizontal. So now if I tilt my head a little like this, then this piece here is what? Less. Okay. Now let's see if we can understand these phenomena. So this one here, I heat up a gas, and then what's supposed to happen to it? It just rises forever. Yeah, right? It rises and it rises and it rises. So it gets to there, right?
It should be starting to do a sonic something, so it has to back up.
Well, it depends on whether or not, this is happening adiabatically. It depends on how the fluid actually moves. If, for example, I had a cold piece of fluid here, like let's say I had a really cold piece, what would it do? Compared to its neighbors, if it was colder and more dense at the very top, just sink, right? So you could also imagine a world hot goes up and cold goes down. That's fine. What's that called? So this is the convective side. Okay. Now in this place here, where we've accurately drawn that it has a negative slope, so we forgot that, maybe just a I. Okay, now what happens to fluid here? As a parcel of fluid here rises.
Density is going down.
Density is going up. Weirdly, right? So density goes up as you go out. And so as this fluid parcel rises, it looks around and has the restoring force of gravity pulling it back down. That makes sense? And this is where we get waves.
Gravity's pulling back down, even though the density.
Let me show you. I'll show you on the laptop.
Because it's so dense. Convection.
What?
Because it's so dense, that's why gravity pulls.
Well, just dense compared to its neighbors, right? It's not like it. Oh my god. Oh,
So,
Oh,
well,
third time's the go.
yeah, I'm just holding it. All right. Oh, it works. Let's go. All right, look at this one here. This is temperature. Temperature and density, we're gonna kind of like hand wave, they're gonna do the same thing. Okay, they decrease. This is altitude. So in this section here, right, the d rho dz greater than 0. Right? This is the convection zone. So this is where the bottom of the ground is hotter than the top of the ground. What about in this region? You can't really see it, but it's tilted over. Once it's tilted over, it's stable to convection, and only gravity waves are permissible. So any perturbation as you climb up, okay, this here is hotter than the neighbors. So as you rise, hot air is trying to rise, it's going into a place that's even hotter. So it sinks back down. Right? And similarly, if you started up here and you were kind of hot, but you know, you were maybe not as hot as your neighbors, so you start to sink, you're gonna end up in stuff that's pretty cold. And it's gonna push you back up. Gravity waves. Here, convectively stable, right? And you could have like stuff that goes all the way up and then back down, all the way up and back down. And then in the tropospause, it actually turns around. Right? So each time you see a word like pause, this indicates a location in the atmosphere where conditions are changing. You've heard of something maybe called the tropopause, or the stratopause, or the mesopause. These are boundaries in the atmosphere. They're not like places with a ticker tape or like a thing that you can cut, right? It's like a rough region in the atmosphere where something is occurring. So there's something called hygropause. Hygro being like, think in your mind, like water. Hygropause is the location in the atmosphere where water tends not to rise past. What that means is as it rises, it's mixed into the atmosphere, mixed, and then it gets cold enough that it uniformly condenses out. And what we find is that the abundance of water is kind of constant relative to the density. And then all of a sudden it gets cold enough that it condenses out and it just cuts off and it goes basically down to 0. That's called the hygropause. Okay. Happy? I'm sorry that I messed up that as well. Thanks for catching. Cash money? Okay, that's all I really want to do with internally stratified waves.
Can I ask one question?
Yeah.
What's the runaway thing you're talking about then on this graph?
Here. Starts at the bottom, it's hotter than its surrounding. It just keeps going until it's not hotter than its surrounding.
Oh, at some point, so here we actually have where that occurs.
Yeah, I mean, in practice, right, this is probably not quite steep enough. Remember that what we're doing here is very hand wavy.
Okay.
Right, because we're still doing these internally stratified media. We haven't even taken into account the fact that this is a viscous fluid, right? We've made a number of approximations. So when we first started doing these internally stratified waves, we said that there would be small perturbations. Okay. So obviously, if the thing is convectively unstable, that's not quite accurate. But the first approximation we can use, like we said earlier, in this part here, is to think about stable stratification and then some modification to it. Right? And what we're going to do throughout the course of the rest of the semester is continue to take sort of the smallest approximation, throw away terms we don't like, see if we get something that in general represents what we want. And we're going to use a number of these individual cases and sort of patchwork them together to explain the variety of phenomena. Cool? Okay, beans. Beans of cool. Let's completely shift topics. So if you're wondering where we're going right now, we are going to consider the fact that I do not believe the Earth is rotating. I think it is a conspiracy, and there is no evidence that the Earth is rotating. Is that correct?
Right now, sure.
Right now?
That's what you said. You said you have to pretend it is.
No. I never said pretend. I told you this is how I feel. These are my feelings inside. It's untrue. The Earth isn't rotating.
Your feelings are valid.
My feelings are valid. Incorrect. Incorrect. Feelings are not valid in the classroom. Okay, so if I have vibes and I'm like, yo, it totally doesn't feel like we're rotating, what do you say to your friend who's in a physics class with you? What?
What?
You say that's a stupid idea, right? There was certainly a time when that was taken seriously. Right? When was that?
They were in conflict church. Saying the sun rotated.
That's 1600s. Is that what you believe? 1600s is when we discovered that the earth was not flat.
Maybe with boats.
With boats. What is the original evidence that the earth is not flat?
People sail maybe across to somewhere else. How could you get somewhere else? It was
Boats don't even, I mean, boats fine, but that's not what we need. There's an easier way to do this.
a sun and a stick.
A sun and a stick. Good, where?
In the equator.
Good, where?
Wasn't it like Egypt?
Good, where?
Well, they used
Under
the
the sun.
monoliths and it was like 20 kilometers apart, and then he figured that would be the.
You're almost there. Use the obelisks in Alexandria, right? Which is very near the equator, like you said, and the ones with his friends in Greece. And they said at agreed upon time on agreed upon day, let us measure the angles. And they got the size of the earth to within like 50 kilometers. So the idea that Christopher Columbus didn't know how big the earth was is a lie. He in fact did know how big the earth was. He had two versions of this calculation, and he said, well, let's just hope that it's kind of smaller. Let's hope it's not this massive ocean in the way. Maybe we'll find something along the way. Right? But we also have to remember that that story that you're told about Christopher Columbus, that excludes the fact that what was the first Europeans to make it to North America? The Vikings. In what year?
Long time before that, right?
Yeah, like 600 years before that. Okay, so they knew there was a continent here. It's a lie. Christopher Columbus did not strike out thinking the Earth was flat. We've known that the Earth was not flat for something close to 5,000 years. Not 500, 5,000. Okay. Now, did we know that the Earth was not the center of the universe? No. There was no reason for us to believe that it was. We talk about this in Astra 1000. Okay. A heliocentric viewpoint differs from the geocentric viewpoint. The only way that you can tell the difference in them is when you start watching the motion of the stars in the sky and you lack parallels. Right? And you think, well, we look around, we are not moving, or it appears that we're not moving because nothing in the background is moving. As I walk around the classroom, you all move relative to one another because I'm close to you. They assume that stars must be relatively close to us, so bright, had no idea of the scale. Right? Okay. So, Earth round. Earth spinny. Known for a long time. Long time. What is this?
Two different coordinate systems.
Yeah, let's go. This is a coordinate transformation. Okay, from a frame O. And instead of doing X, Y, Z here, we're just gonna go ahead and we're gonna say 1, 2, 3. Okay? And 1, 2, 3 is just arbitrary directions in real space. Right? And one thing that we want to think about here is this is the origin versus some point. Okay, so this is some P place that you're considering, and this is the new origin. And the new origin can, of course, be some physical translation away. So that is a Galilean transformation of moving the origin from 1, 2, 3 just over here. And then you'll also notice that perhaps you've done a little rotation. Okay, and so the rotation here puts 1 prime, 2 prime, and 3 prime in a new location. And maybe it spins in its new location. Maybe it's spinning around some axis, right? So you get the velocity here in your inertial reference frame. And that is going to be equal to the combination of quite a few things here. Okay. This U, like we try to do with most of the fluid dynamics, this when it's big, it refers to sort of the bulk, and the little u refers to the fluid properties themselves. Okay. So this one here is the fluid velocity. This one here is the bulk velocity of the frame. This is the fluid velocity in the rotated frame. And this is the angular rotation with respect to the new frame. Right? This is the cross product between.
What's your prime one more time? It's the velocity of the what?
In the new frame. The velocity in the new frame. So this is the velocity in the old frame. Must be equal to the velocity which the frame is moving with, plus the velocity in the new frame, plus the rotation of the new frame, times the location of the time cross product within the location of the new frame. So I might say, all right, here's what we'll do. I know. It was a lot of work just for me to get that down, but this will be worth it.
You see omega is the rotation of the frame.
I'm gonna write them all on the board. Because that I think might help. I wish they just had like a one button, you could like click like an etch a sketch. You know,
No, they do.
maybe a smart board, the smart board's like an instant erase, unless, right?
I think there's much.
Because I read so much. Why do you guys require me to teach you so many things? Less yapping, okay. So primed is in the new rotating and moving coordinate system. Okay, so you have something essentially which is like this. So this thing here, this is the new location to x. Okay, and something like d big X dt. That's big U. All right. And it rotates around this thing. You can't quite see it up here, but let me just write it up here. This is rotating around some rotational axis. Right? So that's the rotational axis. So you can differentiate that. You'll get this U down here. And that's the way that we're going to represent the difference in the rotation. But the thing that I really care about, because I'm a physicist, is not just the velocities, but the forces. Now, what is the force? Simplest way of talking about forces? What? M times A. Okay, so the force is mass times acceleration. So I should really consider here whether or not this new frame introduces any accelerations.
Yes.
How do I do that? Correctus mectus, right? That's this thing. let's do it as a family, okay? A. That's du dt. Okay, or ddt of big U plus U prime plus big omega crossed with U, or sorry, with X prime. Now that's a little confusing. I recognize that, sorry. But that's where it's like, so fuck it, right? Okay, first one's fine. We're just gonna write that d big U dt. Right? Second one, what do we call that?
Du prime dt. Is that okay?
You know, you can simplify it just a little bit. That's correct. That's correct. It's A prime. Okay. Now the third one is gonna throw you for a loop. You're not gonna like it. Okay. The third one is 2 omega cross U prime plus d omega dt cross X prime plus omega cross X prime. Fun, right? If you want, you can do that one as a homework problem. You want to? That's some nice vector geometry, trying to prove that. Does it make sense why that might be the case? Du prime, but this is of course a multiplication. So as we take the derivative with respect to 1, we'll do the product rule, right? But this is a weird product rule, of course, because they are cross products with one another. So you have to think about how they line up. Okay. Okay. So now we have something, this is in terms of A, okay? The new acceleration, and so therefore the new forces, they're gonna have names. Okay? So this one here, this is the acceleration of the frame with respect to the unchanged reference frame. Right? That's this one here. This one here is the acceleration of the fluid seen in the non-inertial frame, A prime. Right? What's this one?
How much the angular rotation changes velocity?
Yeah, something about the velocity, right? So there's something here about the velocity and the frame. Okay, this is called the Coriolis. Acceleration or the Coriolis force when we stick it in the force term. Okay, and we're going to describe what that means in a few seconds. What is this thing?
How fast it's rotating? In that new location within the frame.
Yeah, these are accelerations due to the rotation of the frame. So these are accelerations, due to non-inertial frames. Okay. And this last one? That's right. It's a centripetal acceleration. Now, could you have guessed those? Do you want me to show you how you could have guessed them? Okay. So let us assume that the frame is rotating. But let's assume that the frame rotates at a constant velocity. How can I make each of the terms go to 0? Well, the first one here, I can make this go to 0 by making u equal to 0. There is no Coriolis force when I'm not moving. This is the deflection force that only happens to things in motion because the ground underneath their feet changes respective to where they were originally. So as I throw a ball, right, the earth itself rotates underneath that ball because it's not tied down, and therefore it will appear to curve. This is the Coriolis force. No motion, no Coriolis force. Next, this is an acceleration due to non-inertial rotation. That is to say, if you are rotating at a constant rate, this disappears. If you're speeding up or slowing down, you have an extra term that you need to consider. Okay? This term disappears when you're standing at the pole. Because here, x, if it's 0, this whole thing disappears. So when you are standing on a merry-go-round, if you stand at the very edge versus if you stand in the center, this fictitious force flinging you off the merry-go-round appears stronger as a function of your distance from the rotation axis. So therefore, this is your centripetal acceleration. Right? This one almost always coming with you. This one only coming with you when you move fast relative to the speed of the earth, right? Over time scales that are important. This one only happening if the earth is slowing down, which hopefully not slowing down fast, right? Do you see the terms now? They kind of look fucked, but they're not that fucked.
What was that first thing again after the DUDT?
Here,
Yeah, that what was that one again?
this is just the acceleration. This is the acceleration measured in the rest frame. This is the acceleration measured in the frame by an observer in the rotating frame. Okay. Okay. So I don't want to write it. So here it is. Go cash. Okay, I don't want to write it, so I don't have to. Boom, boom, boom. Look how fast I am at writing. Let's do the bottom equation.
Air pressure gradient,
Good.
primes are we on? Do I mean it's in the other frame? The prime on the gradient stuff.
Well, here's the primes, right? This isn't a rotating frame, so everything's in the rotating frame.
Pressure, gravity, right force.
Good. Body force, good. What else? Yeah.
Just the actual name for the d omega cross x prime, is that some kind of like,
This one.
yeah, is that like you?
It doesn't have like a fun name. This is what we would call the non-inertial acceleration term. But I think in the book they call it. Yeah, angular acceleration due to the non-inertial term. Something like that. It doesn't come up frequently, so I don't think it has a better name. Good, what else?
centrifugal
Where?
there next to the.
This
The
one?
omega cross. Yep, there,
This one?
omega cross X prime.
This one is actually the centripetal acceleration. Centrifugal is not a force. It's difference in terms, it doesn't really matter in the long term, but we're gonna use centripetal here. Which is this one. Centrifugal being what you feel as an observer, centripetal being the fictitious voice. Just as it's in. What's this one? Coriolis.
Is DU/dt the translation?
What?
Is D big U? or
Oh, this
dt?
thing.
Is that translation?
Yeah, that's the motion of the frame, the acceleration of the frame itself. They don't all have nice, fun names and terms. But in practice, we're gonna write them all out. So before we were doing stuff like, ooh, pressure gradients, and everyone was like, oh, I'm getting it, pressure gradients. And now it's kind of like, what the fuck? The rotation of the speeding up of the rotation. Okay. So they're gonna have sort of some weird feelings until we start to apply them. Okay. So one of the first things we're gonna do is once we have Navier-Stokes like this, okay, we're gonna apply it to a physical system. And the first physical system that I want you to think about is, say, an atmosphere like the Earth's, okay? And in particular, I want you to think about sort of global scale climate dynamics. So, you might have something like this. That's quite large compared to the scale of the atmosphere, right? The whole planet's like that, and this thing's like a sizable fraction on it. So, like the state of, I don't know, Iowa might be under here. Big, big scale. So if we go to something like this, okay, can we say to different parts of these equations? Can we say whether or not this term is bigger than this term? Is this term bigger than this term? Is this term bigger than this term? Is there an obvious choice for which term you would make an argument for deleting? Or saying this one feels negligible?
That sounds an operator.
Excuse me?
What, a mu?
This one? This is the diffusion of velocity by viscosity.
Oh, it is.
What page is that equation on? Says that's not your strokes, just written in a different way, correct?
This is Navier-Stokes, yeah.
Okay, just
With more terms, yeah.
Gotcha.
Yeah. So which one can I set to 0 in the context that I just showed you? What?
You're at the equator? The pictures.
Wouldn't you keep that one? Cause
Yeah.
you're still at the edge of the earth, like.
So this is an example of what we call the equipartition surface. And what this means is as this object is rotating, at the very top, you have very little centripetal force throwing you off. So therefore you feel the full weight of gravity. As you move towards the equator, you're actually being flung out. So therefore you have a reduced gravity. Okay. So sometimes they say there's an equipotential surface, and G is not in fact pointing towards the center of the Earth, but a little bit off. Not quite to the normal. Some other people just take G and they just modify that slightly. based on your location, right? So depending on whether or not you're at the equator or whether you're at the North Pole, you might just take the 9.8 that you know and love, and you may just dial that. Right? You never thought about that.
But was it equal parts where they said it? It's just like a relationship between two things and they said it equal, said it equals 0 or something.
I'm saying
Partition.
equipotential.
Oh, thank you.
I may have said equipotential. My voice is sometimes enunciated, not good. But I meant equipotential. This is a surface of equal potential. That is to say, instead of it being circular or on the surface of the sphere, all points are the same, a new shape is formed. Right? That bulges out towards the center. And it's shorter. Okay?
That is because it's rotating, right?
As it's rotating. Why do they launch rockets in Florida? What does that do for us?
Right, that's how we get the gravitation.
We save millions and millions of dollars by just letting the Earth fling us off. Right? Now, Hawaii is technically more southern than Florida. Why don't we go to Hawaii? Watch them.
Spin still faster.
I'll be two backwards.
Why?
Flat.
You're almost there. You're like 90% of the way there. How do you get to Hawaii? Oh, fly! Right? Imagine if you wanted to build a rocket. You have to ship everything by boat. Right? There's no trains. Did you know that trains and like trucks are what carry your rocket from Ohio where it's built to where it's flown? So if, for example, you have something like the JWST, which is a space telescope that went up a few years ago, that flew took off from the Canary Islands. Where that is. What? The Canary Islands are kind of like north west of the tip of Africa. They're like somewhere in between. So here's Europe, and here's Africa. They're like, okay, right next to the equator. They have a launch facility. It's on an island. Okay, so now I'm walking back the Hawaii thing. But let me tell you about how fucked it was to get there. Okay, so the first thing that you have to do is to build it. So it's all built in the U.S. Then you got to put it on a boat. And then you got to make sure that boat arrives safely at its destination. So it might have to pass through the Panama Canal to pick up, XYZ from here or whatever. And not fast. If we can take a train, then we can just put stuff on a train, bring it all the way down to the bottom of Florida. You save money. Ran out of time, but I want to explain the curly Q. You can now do this with the Coriolis term. Can you explain why they could turn right or left? That's your Monday homework. Monday? Yeah, tonight. I want it done by Wednesday, so you can all explain, right? I'm gonna post homework. I think it's 8 or 9. I forget what is up next. What? Should be 8. So what we'll do today, let's see. Move this away. We will finish up this discussion of rotating frames, and then we'll just talk about like different vertical structures, and we'll talk about different waves. I think where the heck did this go? Why does nothing show up when I need it to? Oh my God. Okay, well, I don't know what the schedule is, but you get the idea.